Okay, gang, so here's the next example we're talking about in section 4.5 where we're working on optimization problems. In number 20, read over number 20. Hopefully you got your book open while you're doing this, right? The idea is, according to postal regulations, a square-based box, such as this, right? Notice I've got the dimensions x by x, so the base is a perfect square, and the height is y. And it says that we want to find the dimensions of the largest possible box we can send through the postal service, subject to the condition that the length plus the width plus the height cannot exceed 108 inches. Okay, so if we want the largest box possible, let's just take that whole sum and actually force it equal to 108. Okay, and that's exactly what I did right here. Now notice, a little bit different from the previous problem that we did, right? The quantity you want to maximize right here is the volume, but again, notice it's got two different variables in it, and we don't do this, right? We haven't done this before, and so we also, here's something else. We also have a constraint, okay? Subject to the condition that the sum of these three things has to be 108 exactly, right? So a lot of the optimization problems that we typically deal with, there's a quantity you want to maximize or minimize, but then you're going to be subject to some kind of a constraint, okay? So here's what we do. Since we're not allowed to use two different variables before we take the derivative, be careful now, this is not an implicit differentiation problem where you can use the method of partials, okay? It's not like that. What I'm going to do is I'm going to take the constraint equation and I'm going to solve it for one of those variables. It doesn't make a difference which one you solve for. I'm going to solve for y because it looks like it's the easier of the two to isolate. Find what that value is, and then force it into the original function that you want to maximize or minimize. Okay, so here, okay, so I took my constraint equation, I solved for one of the variables. Now I'm going to force that variable into the volume equation. Okay. And so now my volume is in terms of just one variable only. Now we can go through and we can take the derivative, we can look for the critical numbers, just like we did with the previous problem. All right, so notice again that this is a polynomial, and whose domain is ordinarily all real numbers, but we can't use all real numbers just like the previous problem, right? It's a real world situation. So you're not going to be able to use negative numbers here. So we're going to have to cut out everything to the left of zero, as we say, right? You can't go too far out either. If you go too far in the positive direction, right, this quantity right here will wind up being a negative value as well. All right, so the polynomial that represents the volume is this, but only on this interval. Okay, so we've got a nice continuous function. It's defined on a closed interval. This is a section 4.1 problem, just like we talked about in the previous example. Find the critical numbers. Then evaluate the original function, or right here, evaluate the original function at the endpoints and any critical numbers in between, right? And then you're going to generate that list of numbers, and whatever the largest number on the list is, that's going to be your maximum value. Okay, so you verify, work along with me now. Okay, take the derivative of your volume function. I'll go up here and do it. Now, it's another polynomial, so it's not going to be undefined anywhere. You're not going to get any critical numbers that way. The only other way you're going to get critical numbers is to solve for this. Okay? Verify that this will happen. Okay? For these two numbers. Now be careful. Again, appealing to section 4.1. Is it possible for x equals 0 to be a critical number? No. Why? Because it's an end. Okay, look, it's at the end. Remember, the critical numbers have to be in between the endpoints. If the function is defined on a closed interval, then the critical numbers have to be in between the ends. So this cannot be a critical number. And when you think about it, it wouldn't even make sense in the context of the problem anyway, right? Again, look, if x is equal to 0, the whole box collapses, right? So that's not going to work. But this will work. 36 is between 0 and 54, okay? All right, so I'm going to take my one critical number, and then I'm going to evaluate the volume equation at both ends, and then the one critical number in between. Okay? Now you verify at the left end and at the right end. You're going to get 0 both times. What are you going to get for 36? Well, I actually worked that out for us real quick. And that winds up being, oh, I had it written down. I think it's like 49,000. I'm just going to approximate it. I had it written down on another piece of paper, but verify that. But obviously that's the largest number that's on the list. So that's going to be your maximum volume. But according to the directions in the book now, it says, what are the dimensions that are going to make this happen? Okay, well, we've got x is equal to 36. Okay, so you got a square-based box like they told us to. What's the y dimension? Well, gang, look, you can get the y dimension right from here. Take your 36, force it into the equation right here, 108 minus 2 times 36. That'll give you the y dimension as well. Verify with your calculator. That's going to wind up being 36 as well. So the box actually winds up, in this case, the box winds up being a cube. Okay? Verify my calculations. Check this for me, gang. Like I said, I thought I had it written down on this piece of paper, but check this for me. I'm just approximating. And then make sure you understand what's going on here, and then we'll start on some more examples. Okay?